So thank you so much for joining us. I'm Michael Lee. I'm the founder of the Data Incubator, and we're really excited to have you with us. Today we'll be doing data science in 30 minutes, and it will be doing both it'll involve both myself as well as my colleague Christian. Say hi, Christian.
Hey there, I'm right next to Michael. I'm the lead software developer here at the Incubator, and it's good to meet you all.
Okay, so as I'm sure you all know, you've gotten the link to the GitHub repo. I am just going to share my screen so that you guys can see that. And all right, cool. So we're going to be talking about neural nets today. And as you probably know, we run a data science fellowship. It's called the Data Incubator. You can follow this link over and read more about us on our website. It's thedataincubator.com. And then just a little advertisement. We are actually doing our application for the spring fellowship, and the deadline is coming up in 2 to 3 days. So if you're interested, you should click on that link, come down to apply, enter your email to apply for the fellowship, if you haven't already. But back to our regularly scheduled programming.
One other thing, just to plug for the Q&A session.
Oh, yes. That's right. Thank you for reminding me, Christian. There is also, if you are on the YouTube link, that is, if the page looks like a YouTube page, there is some information on it about the Google Hangouts or a Google Plus page that you can go to, which will allow you to participate in the Q&A session. So we're just going to be talking through this material. Feel free to add in questions as you have, as they come up, and we'll try to answer them as we go through our little webinar. And we'll obviously have a lot of questions at the end that we'll be happy to answer. So anyways, as I said, we run a data science fellowship, and one of the most popular topics in data science and machine learning these days is neural nets. So you can think of a neural network as something that's metaphorically like your brain. There's a series of nodes called neurons, and they form layers, and those layers might activate, and the activation is sort of like an electrical charge firing through a neuron, and that will propagate a signal over to the next to the next set of neurons in the next layer. Now that's all a little fuzzy, so let me maybe draw a picture for you or show you this picture here. So this is kind of what a neural net is like. There is a series of inputs. These are the neurons. They're connected via weights, and we add them up using an inner product. And then the part that's interesting about this, the part that makes this non-trivial, is that their input into the next neuron is via a nonlinear function. This is why this formula, the inner product down here, that is just a simple linear model. The thing that makes this interesting is the nonlinear aspect of this, where we apply what's called an activation function to the inner product, and that's what determines the value going into the next layer of neurons. So the activation function that you see here is just a Heaviside function, and that's sort of a function that's often used. You might also see a logistic function or a sigmoid function, and all of those sort of have the same effect of ensuring that the values are in the neuron, the values the neurons can take are always constrained. Sometimes, in this case, between -1 and 1 for the Heaviside function, and if it's for the sigmoid function, it'd be between 0 and 1. Now, I've been skipping around a lot, so let me go back and say a few words about the perceptron and the most basic sort of neural net. The perceptron is, again, it's a neural net where the activation function is the Heaviside function. You take a series of inputs, we might call them V, and we pass it through this function. We'll take the inner product of the weights and V, and then we get out a term, and we apply this activation function to it, and that's the value that we're trying to predict, that we're predicting. And So this is all pretty much straightforward. Let me show you, let me try to illustrate this in a very simple example. Here I have a little bit of Python code. And the Python code, if you ran through the installation instructions that were in the GitHub repository, it's in the README section. If you ran through those installation instructions, you should be able to run this IPython notebook. And the results you'll see are actually quite clear. What we're doing is we're generating some random values. This is going to be 100 data points, and each one takes on 2 possible values. We want to see if, we're basically trying to color the map. So if these things are on the upper left-hand corner, we're going to make them black. If they're on the lower right-hand corner, we're going to make them white. And that's what we're doing here when we set the label values. We then draw the scatter plot accordingly and can see what the data looks like. Again, pretty straightforward. Now, as you, if you know a little bit about machine learning, you probably know that the name of the game in machine learning is to try to learn this relationship. In fact, this is what you might call a classification problem. We're trying to, given these data points, trying to figure out which, I'm given another prediction, whether it's more likely to be black or white. And of course, you can tell that there's probably a line down the middle here, which is going to predict that. And so let's take a look at what that line would be and how we would learn it using a neural net. Now keep in mind, of course, that this is a lot like many forms of regression that you may have seen. So I'm going to show you a formula here. And this formula probably looks a lot like linear regression. Or more, perhaps to be more precise, it looks a lot like logistic regression. In fact, actually, this is effectively what we're doing. So you have the value that you're trying to predict, the sigmoid of the inner product here, and this, you remember, is the inner product. And we're going to add up all the error terms, and that's going to be our objective function. We're trying to minimize error. And then whenever you see in machine learning that there is a function that you're trying to minimize, the answer to this problem is almost always going to be stochastic gradient descent. So anybody who's done a little bit of optimization or a little bit of applied math will probably know that to minimize the function, what you do is you take its gradient with respect to the parameters you're trying to solve for. And in this case, since we're trying to learn the weights of this model, W, we're going to take the gradient with respect to W. And here it is, a little bit of math worked out for you. Grad E, grad W is the sum of, well, you just apply chain rule. It's pretty straightforward. So the relationship between E and F is well defined up here, and its gradient, with a little bit of calculus, is quite clear. The relationship between F and U is also quite clear, because you see F and U, it's just a sigmoid function. So the derivative of the sigmoid function is F1 minus F. And then finally, the last little bit down here, oh, I can't highlight correctly, is just the gradient of U with respect to W, but because U is just the inner product of W and X, the gradient is just X. So I hope this convinces you that this gradient is very easy to compute. And then the answers for how you update the weights is you start at some arbitrary point. You can set it to 0. You can set it to be a random point. But what you do is you slowly take, at each iteration, you go downhill. You compute the gradient, which is this, which is this, and you go down, hence the negative sign, and you multiply that by a constant. And the idea of the constant is that it's supposed to be small, or maybe even decreasing with the iterations, but you're moving down this gradient in time. So that's a lot of math. Let's try to draw this out in a slightly more concrete example. So we're going to just write a little bit of code that does all the math here. So just to prove to you that I have nothing up my sleeves, we're going to set the initial weight to be this. We'll set our learning rate. This is our eta. And then we're going to set the number of epochs. otherwise known as how many times we're going to try to step down this gradient before we stop. And then this is, of course, just a loop that goes through each of those epochs. And you'll notice that we're going to make a prediction. This is basically our f. We're going to then compute the value of our derivative, right, that we're calculating here. We then compute what the corresponding update value, which is this term, should be. We multiply that by our learning rate, and we decrement our weights by that. So this is literally how we're going to perform our weight updating. Now, we want to actually see how the updates happen. So we're going to save off the normalized weight history. And we'll talk a little bit about why it's important to have a normalized weight history later, or why the weight history should be normalized or not later. But for now, let's do that. Now, the predictions we're going to make are actually based on the model, right? The inner product of the model and the training vector. And then we want to see if the sigmoid function applied to this is greater than 0.5. Because that's basically computing f of u, or f of w and x, and looking at whether or not it's greater than 1/2 or less than 1/2. If it's greater than 1/2, we're going to assign it one color, I think black, and if it's less than 1/2, we're going to assign it the other color, white. And if I haven't lost my place, let me run a little bit of code. So you'll have to take my word for well, no, you can actually check for yourself. The weights here start at 1, 0. So 1, 0. And they start moving. And you'll see what's happening is that they are going to start moving here, and they eventually converge at minus 0.5, 0.5. So if you think about it, actually, let me show you a plot of what that model looks like. Here's the plot of the model. So again, the black points are here, the white points are here, and this line divides it perfectly. And if you think about it, the gradient of this line, the normal of this line, is so it's going in the direction minus 1, 1, right? If you think about what the coordinates are, it's going up and to the left, so it's the normal line, the perpendicular line, is normal and up and to the left. Up and to the left, and therefore it's slow. It forms a vector minus 1, 1. Now, of course, because all we're trying to do is to find a normal to this line, it can be scaled, right? So it could be minus 1, 1. It could be minus 2, 2. It could be minus 3, 3. And you know that all those are equally valid perpendicular lines to this separating, what I would call a separating hyperplane, or this plane that separates the points. So you'll see that that minus 1, 1 is exactly what we're looking for when we find here, except that because I normalized it, here I'm dividing by the sum, so I need to ensure that the absolute value is going to sum up to 1. I end up with minus 0.5, 0.5. And that's, so you expect an answer that's sort of minus xx. You do find that it's minus 0.55 because of the normalization constant, or the normalization scheme we chose. And you see that the points are basically approaching that. And as they get closer and closer, they start taking smaller and smaller steps because we're nearing the right answer. So this is how the weights converge with time. And here's the picture of the model. Now, this is a pretty simple model. You really didn't need a lot of neural nets to be able to get this far. In fact, a simple logistic regression would work. But my colleague here, Christian, is going to talk more about how more complex neural nets will work. And without further ado, I'll hand it over to him. Yep, let me.
Cool. Hopefully everyone can hear me now, and I'm going to share my screen. I first wanted to reference a question that I believe Stefan and Carolyn brought up. Apologies for closing yours early, Stefan, but in regards to the environment.yaml file, I believe it does work on OS X. However, I did forget to include scikit-learn. I just pushed that change up after making it maybe an hour ago. I forgot to push it. So apologies for that, but the environment.yaml file will now install everything you need if you download this repository from GitHub. So if I show the screen, we should hopefully see. Great. Okay. Right. So I believe Michael mentioned kind of the high-level structure of a neural network, and what I'm going to be doing is basically giving an applied example here through a very cool neural network called word2vec that allows us to produce some really interesting non-trivial results on a wide variety of different unstructured text data. So again, as Michael mentioned, here's sort of the core structure of a neural net. We have our input layers, we have our hidden layers, and we have our output layers. And in terms of the differences in training, they're actually very similar. As Michael kind of implied, stochastic gradient descent is always the thing you're going to be using, or very often rather, the thing you're going to be using to train a lot of different kind of like classification style models. Neural nets are no exception, and the particular variant of stochastic gradient descent that we use is called backpropagation. So in the interest of time, I think we want to move straight into this model word2vec and what it does. So word2vec is essentially a model that takes a vocabulary. So you can think of that as just, 10,000 English language words. It takes a vocabulary and maps that vocabulary into a vector space. In that vector space, words are clustered based on their similarity. So at its base, word2vec is another clustering algorithm. You might have heard of latent Dirichlet allocation as another very useful sort of like natural language clustering model. Word2vec is similar in this way, but we already have models that do this. What makes word2vec more interesting? Well, for one thing, it's very good at what it does, and it trains very quickly. For another, and this is kind of one of those like sort of deep learning, weird artifacty properties that make neural networks kind of crazy, we can actually compute analogies. So for example, in English, if I were to say, man is to king as woman is to, we'd all kind of know that would be queen, right? That's a very intuitive thing for us. We immediately come up with that analogy, no problem. Well, in this vector space that we get back from word2vec, we can actually say, well, if we take the vector for king, subtract the vector for man, and then add the vector for woman, what's the closest vector to that resultant vector there? And the closest word vector mapping we have is actually the word for queen on the well-trained vector space, as I will show you momentarily. It's really, really cool. So actually, one more thing that word2vec does really well is it's actually also a language model. And for those of you familiar with NLP, it's the sort of typical, given a series of words, can we predict the next word kind of thing. But as it turns out, word2vec is actually also very, very good as just a straightforward language model. So to take a look at this, let's use a tool called GenSim. It's Python-based. It relies on NumPy and SciPy kind of as default. If you have C installed, or C compilers at least, you can actually build even faster, further optimized versions of these models, and that really speeds up training. It's really helpful. But if you just have NumPy, GenSim also works just as well. And the first thing I want to do here is quickly just take a look at a pre-trained model, a model that I think Google researchers built on the Google News data set. That's about 1.5 gigabytes, so it does take a little bit of time to download, but it is well worth the download. It's very cool. So we're going to load up that pre-trained model and take a look at the vector space that we get back from word2vec and see some cool kind of analogies and clusters. So the first thing I want to show you is just the cluster around king. So what kind of words in this Google News trained vector space are similar to king? And we can see here, there are words we pretty much expect. Maybe we could do some stemming here, or Google could have done some stemming and it would look a little bit better. But it's pretty much as expected. Queen, princes, ruler, sultan, kingly. And then actually, another thing Google did here was take some simple bigrams and turn them into additional words in the vocabulary. That's a common trick that's used in NLP type analyses. And this is basically your typical cluster, right? LDA would do the same thing. However, let's try that kind of vector computation I was talking about for an analogy. So let's do the exact one that we said above. Let's take king, subtract man from it, and add woman to it and see what comes up. And as we kind of would hope from a reasonable analogy, queen is the most similar word to this resultant vector, which is really cool. And we also see that monarch is kind of common, which is interesting. If we were doing this actually live in a kind of exploratory fashion, the next question we might reasonably ask is, well, what happens if we just take king and subtract man? Are we going to get any kind of like gender neutral notion maybe of what a king is? And it's not particularly great. I actually looked up Pansy Hoach, who is like the daughter of a wealthy businessman. But we do get some interesting things a little bit further down the list there. You can see monarch, again, is kind of gender neutral. Kingdom is sort of like some notion of kingliness without humanity. Similarly for palace, it's something that it's associated to with a king, but not necessarily with a human quite as much, maybe. So yeah, this is the kind of thing that word2vec does really, really well. And it takes a lot of data to do in general, but well-trained, you produce extremely interesting similarities. So I'll quickly talk about how this model is trained and what the neural net actually kind of looks like based on the structure we talked about before. So again, we have an input layer, a hidden layer, and an output layer, where the input layer is a series of 4 one-hot encoded words. So a one-hot encoding is essentially, if we have 1,000 words in our vocabulary, we say, okay, let's sort them in alphabetical order. The first word is going to be word 1. Second word is going to be word 2, up to word 1,000. Then we generate a whole bunch. We generate 1,000 vectors, each of length 1,000. And we say, okay, the vector that's going to correspond to word 1 is the word that has index 1's value as 1. The rest of the values is 0. So it's a very, very simple encoding. And actually, real word2vec uses a much more optimized sort of tree structure to store its word encodings for faster computation. But it's sort of illustrative to understand basically how the model's working at a high level. So we get in these 4 essentially meaninglessly encoded vectors. And the first thing that happens is we transition into the hidden layer via this matrix, as you can see here, W. And what that mapping does, you can see it's a V by N matrix, where V is the size of our vocabulary. So if we have a size 1,000 vocabulary, that would be 1,000 by N, where N is some number of our choosing. And it's going to actually correspond to how the dimensionality of our vector space. So a typical number is about 100, 100 to 300. I believe that Jensen by default uses 100. So we map these one-hot encoded vectors into this vector space of length 100. And that's actually, as it turns out, what we're looking for when we're looking for that vector space embedding of our words. So word2vec is really interesting because it's an artifact of the model. We haven't even gotten to the output layer, which is one single one-hot encoded word. And again, word2vec is a language model, so it might look something like this. Like the input words might be the quick brown, and our output layer might be fox. That's essentially how continuous bag of words works. We're trying to predict the next word based on the previous words. Or actually, I think in the context of continuous bag of words, it's you get the surrounding words and you predict the middle word, something like that. So the quick blank fox jumps, and we'd expect brown maybe. But in any event, in terms of a neural network, we transitioned into the hidden layer. We then have one final set of weights, a second set of weights that maps into our output layer, maps into that most likely word. However, what we ultimately care about is actually that transition matrix that I spent a bit of time on there, W. And as it turns out, in the setup, the rows of W, as you can see, there are V rows. The rows of W correspond exactly to each mapping of a given word in our vocabulary into our word2vec vector space. And why exactly does a language model compute a bunch of associations between words that we can then do analogies on in the context of a neural network? It's not 100% clear. We don't really know. We understand how the model works. We understand all of its machinery, but there's something kind of happening at that hidden layer that isn't the most clear. And this is why people get really excited, right, about things like Google's Deep Dream, where we kind of look into the middle states of this neural network, or something like this, word2vec, where again, we're looking into that middle state and actually finding something really interesting and non-trivial, and there is some kind of crazy learning going on, right? So without further ado, how can we use this? Because while theory is fun, let's actually see if we can get anything from this, and we can do this very quickly. at least with the kind of hardware that we have here at the incubator. So we have a data set here. It's Yelp's academic data set. And basically, this is a bunch of reviews from Yelp. It's a very small subset of the data, around a gigabyte in size. So again, we're using GenSim's word2vec model. And this time, we're actually going to do a little bit of training. I think I'm going to skip this section in the interest of time. Oh, I can do it? OK, cool. Sure. So again, we're using GenSim. And the first thing that I kind of wanted to point out here is just if we were, as we're going through this, I think the first thing that we thought about here was, OK, well, what about the pre-trained model that we have? Yelp's data set is interesting because it has a bunch of restaurant reviews. So maybe we can look at different types of cuisine. What kind of analogies can we compute on cuisine? That kind of thing. So let's see how the Google News data set actually holds up with some analogies on cuisine before even trying the Yelp data set, just to set a baseline. So looking, here we can see that we're trying to find something that is similar to a burrito without the connotation of Mexican, but maybe in Chinese cuisine. And we actually come up with really good results again. Steamed buns are pretty sort of one of these, like, if you think of the burrito as an emblematic Mexican thing, at least to sort of Americans, then a steamed bun is quite similar. Similarly, kind of for General Tso's chicken, right? Like there's a whole movie about General Tso's chicken, and so on and so forth. So that actually turned out quite well. And actually, similarly, if we take burrito and subtract the Mexican connotation from it, again, we're left with kind of like default American foods, which does say something about the Google News data set. It's kind of interesting, right? But sort of emblematic American foods is what we end up with. So there's that's kind of the baseline that we're working with, and let's see if we can actually come up with anything better or more interesting by using the Yelp data set. So this section is sort of how the model's trained. This image is kind of like what the training looks like as we go through it. And as you can see, the word count increases here, and alpha, our learning rate, decreases. This is a really good trick as you're trying to achieve convergence, as Michael was talking about, to decrease the learning rate over time as you kind of get closer to the minimum of this sort of optimization problem. But again, this is kind of the part of the show where we've already done the cooking and done the training. It took us about an hour on one of our super high-powered DigitalOcean instances to run this training, which is really, really not bad at all. I think on the larger Google News set with a suitably sized cluster, it took about a day to train the pre-trained model we use, and that's really, really, really fast in the context of kind of neural networks in this field. So instead of doing that, instead of training, let's load up the model. We actually included this in the Git repository, so you can load it up yourself as well and follow along here. Our trained model ended up being 200 megabytes, and actually already there's a couple of warning signs. And as we were going through this, we immediately kind of saw those warning signs. In particular, the main one is that our model is small and our data set is small. The Google News data set is gigabytes upon gigabytes of unstructured text data, of sentences, of news articles. This Yelp data set, as I mentioned, is closer to 500 megabytes, a gigabyte, easily fits in memory on one machine, and is not sort of suitably sized based on kind of the recommendations of the word2vec authors, creators, for producing a good model. So the fact that we can actually even store this as a 200 megabyte model is a sort of immediate warning flag. But this is exploratory. This is a very quick thing. And I think the coolest part of this is how quickly we can do this exploration with the tools that we have. So we look at some of the clusters that we got from this pre-trained model in terms of Chinese and Mexican cuisines. And you can see that all these words are kind of already in a cluster here, right, in the model that we trained on the Yelp data. Cool. So let's look at the previous analogy that we did. A burrito that is not Mexican but is Chinese. And as you can see here, this doesn't perform quite as well. Again, I think part of the issue is that our data set's a little small. There are certainly some red flags here. That being said, we see vermicelli noodles, we see beef chicken, which might be some kind of Chinese American dish. We do see a little bit, but it's clear that we're still kind of in this kind of similarity cluster to burrito, and weren't actually moved far enough outside of that cluster, because these are all the top results here are all kind of emblematic Mexican American things. Furthermore, we didn't do the best cleaning of this text because it was kind of like a quick and dirty analysis, which is fine. But so if we look at the cluster around pizza, another kind of common thing you might expect in the Yelp data set, you see that, oh, well, we have pizza with a period and pizza, and that's maybe not what we want to see, right? Hopefully we do a little bit better parsing if we were going to continue with this exploration. But we do see still some interesting clustering going on. Sicilian, Margarita, Neapolitan, those are all pizza styles for sure. Pepperoni is apparently always used in the context of pizza, or very frequently at least, because it's very similar to pizza. But I think one last fun thing that we wanted to show off here was that if you actually look in the Yelp data set, we are playing around with bad pizza in New York. The first maybe controversial result is Grimaldi's. So according to 600 megabytes of Yelp reviews and word2vec, you should avoid Grimaldi's. Take that as you will. So as I mentioned, I think it was pretty clear that even parsing aside, we were using a very small data set. One of the cool things about word2vec is that it actually effectively can be used as an online model, or you can break your training apart into multiple steps. So one really productive next step that we might want to take here would be to actually use the Google News pre-trained vector space embedding, start with that, and then add on this Yelp review data on top of that to maybe get some better mappings for those food words. And by doing that, we then have sort of a bigger data set to start with, but also increase the granularity with what we're interested in. But I think, yeah, if we were to really want to just look at kind of Yelp review data, we need more of it, which would mean we'd have to have a lot more access to Yelp data. We don't have that here at the incubator, although they are one of our hiring partners. I think that covers it from my end, though. Hopefully this was kind of interesting, and yeah, there's tons of room for further exploration with this data set, with a whole bunch of other models, and with word2vec as well, and word2vec on other data sets. So I'm going to stop screen sharing. Okay, and I'm going to say.
Okay, cool. So I think that about finishes it up. If you continue down on the, sorry, if you continue down on the IPython notebook, you'll see at the very end that we have some information if you're looking to apply to be a fellow, or if you're looking for data science training, corporate training partnerships to hire data scientists. You can reach out to us via our website, and the links are on the bottom of that on the neural nets IPython notebook. And now I think we're looking to answer questions that people might have, and I'm happy to just take them. And so again, if you weren't here in the beginning, I made a brief plug. You should probably try to view us through the Google Plus, whatever, the Google Plus event page is what it's called. And if you are on a page that looks like it's a YouTube page, that we have put the link to the Google Plus event page on the YouTube page. So if you look around, you'll find a Google Plus link. Click on that and you'll be able to ask questions. So the first question we have is, do you plan on running a data engineering fellowship as well? I think that's definitely one of the things we're considering, and absolutely something we're thinking about. Obviously, there's a large demand for data engineering. And so if you want to find out more, I suggest you put your name down as an applicant for the data science fellowship, and we'll notify you as we expand and are looking to offer more types of fellowships. I have now just lost the order, so I will start coming from the bottom. According to the image, if there are 2 features, the model has 3 inputs, 1 is a constant. Shouldn't there be 3 weights? So yes, that's right. That's one way of doing it. And in our model, we decided to do a very simple way where we don't have the intercept term. So there's just 2 weights.
No, we centered our data around the origin. So we didn't have to
that's a very good point from Christian. We centered our data around the origin, mostly because we wanted to be able to visualize this in 2D space. There's a question about whether masters can participate, and absolutely. In fact, we've answered this in the Q&A, but if you go look at the Q&A, one of the questions is, are you eligible if you have a master's degree to apply for the data incubator? And the answer is, of course, yes. So there's some questions about, OSX, and yes, so Christian said that we forgot to put in the scikit-learn dependency in the conda in the file. So if you do a git pull, it's already there now, and you should be able to start, or you should be able to install things very nicely. And everything should work. Let's see, the next question is, if you want to participate in the fellowship in New York and work in Boston afterwards, will it work? Yes, absolutely. So we work with a number of companies in Boston. So if you are interested in working in Boston, we'd highly encourage you to apply to the New York fellowship. And then the last question is, are companies hiring for roles outside the United States? And yes, we have a few companies that are hiring for roles outside the United States. So, and we also have a partnership with a company in Malaysia. So if that's what you're interested in, I highly suggest you look for them, look them up as well. There's a question about calculus background versus programming background. I would say it's definitely, both are definitely important. Obviously, the most, probability and stats is probably a more important topic than calculus in terms of mathematics on the math side. But programming is also a very important skill. And I think that the IPython notebook that you just saw is sort of very characteristic of the way our modules work. We have kind of a set up curriculum on a whole bunch of different topics around data science, and we have a whole bunch of what we call mini projects. You can think of them as sort of canonical workflows in data science. And the idea of these mini projects is to teach you how to do a NLP project, how to do a time series project, etc. So there's a question about somebody with a biology background, with a little bit of bioengineering, and whether, I guess the question is sort of, are you eligible to apply for the fellowship? And then are you, and how would they learn more about computer science? And I think the point is that if you want to learn more about computer science, there's tons of great resources online. I would probably point you to our blog, where we have a number of resources for ways to prepare for the application for the data incubator as well as for the program. So that's available at blog.thedataincubator.com. Okay. So there's a question about a CV, and I'm not sure if I can really say sort of exactly how one can, I guess you put up whatever CV you think would be appropriate. That's all I can say. So there's somebody else asked about how our program is harder to get into than Harvard. Yeah, so that's, I think there was a quote in VentureBeat about that. So you can take a look at, I think it's Eric's article. You can Google for it if you're interested in learning more. So there's a question about if you don't have previous experience as a data scientist, what would be would the fellowship be a good kickstart? And yes, I think what we're looking for, and again, this is also on the FAQ, is folks who have a bit of programming background and a bit of stats background, and who are sort of common sense minded. And if you have a little bit of all three, I think you would make a good applicant for the program. As I think we said before, most of the applicants do have some background in both. Which doesn't mean that we've definitely had people come through who maybe started without very much programming background at all when they applied, but then sort of really boned up over the course of the next few months. Yeah, sorry, before they started the fellowship. And so if that's something that you're very interested in doing, that's also something I would highly recommend you try. Would it be appropriate to run network optimizations? So there's a question about network optimizations on neural networks. I think if you explained what your question was a little bit more, I could try to answer it, but it might be hard. So there's a question about Kuala Lumpur. Yeah, so you should go. So if you're actually based in Malaysia, I would recommend you go to the program page for the partnership we have with the Malaysian government there. Oh, there's a question about will I be eligible to apply after graduating? And yes, so the point is we're just looking for people with PhDs or master's degrees. So you can have graduated 20 years ago. You could be graduating 6 months from now. But we do want to ask for people who are about to graduate or have already graduated. So there's a question about instructions at the program. So actually, Christian and I both do a little bit of instructions, and then there are 2 other instructors who are here. There's a question about if you're in the middle of your PhD, should you apply? So yes, you should. You should absolutely apply, but when you are basically within 1 year of graduating. And I think the questions about when should you apply and so on are all answered on the FAQ. There's a question about sort of spatial data science jobs and where one can find them. I think that there are data science jobs all over the place, and I guess I would encourage you to look. Obviously, we actually work with a number of companies that do have a significant spatial component. We'll work with a number of hiring companies that are looking to hire data scientists that have a significant spatial component to their work. So the data incubator may also be a good resource for you, but you can also Google around. So there's a question. I think I'm just going to answer a lot of these in terms of more blanketly. I think there's a lot of people who are of the form, I have a background in X, can I apply? And I think what we say is that we usually look for people with STEM. The most applicants have STEM advanced degrees, so a master's or a PhD, or about to get a master's or a PhD in a STEM field. This STEM includes social science. If you have an English PhD, but you're very interested in data science, we do not preclude you from applying. You do need a PhD or a master's degree, though. And so I guess if your question is, I have a background in X, can I apply? The answer is basically yes. So there's another question about how would I develop more of my programming skills, and there's another question about how would I develop more of my mathematics skills. And I would say if you are looking to develop your engineering or mathematics skills, you should completely go look online. There's a lot of resources, and a place to start might be at our blog.thedataincubator.com. If you look through, there's a bunch of articles on how to become a data scientist, how to get started as a data scientist, how to start thinking about mathematics and computation differently and in new and interesting ways. Okay, I think there's a question about visa status. So yeah, so we actually encourage, we're not limited to people only in the US. We actually are okay with anyone applying. So and we actually have a number of fellows currently, a number of fellows and scholars currently who don't have U.S. work authorization. So if you are interested in data science and you're interested in starting a career in data science and you think that the fellowship or the program would be helpful, I would really encourage you to apply online on our website. Yeah, so again, I think as we mentioned, we have a number of job opportunities. I know we have some in Canada as well as in Europe. I don't know if I have the specifics there, but yeah, there are lots of hiring partners that we work with throughout the world. All right, so I think the questions are getting to be, I think most of the people have gotten their questions answered. So I will bid you all adieu. Thank you so much for joining us, and well, hope to see you guys either as an applicant or hopefully as a fellow at the programs soon. Talk to you later. Bye.